think we can get started. Hi, everyone. My name is Laura, and in this workshop, we're going to talk about closure in JavaScript. And I know that you're all here for this topic specifically, but in order to get into kind of the characteristics of closure, we're going to start by building out our understanding of some fundamentals that's going to allow us to explore this in detail. Our goal is to understand what's happening behind the scenes when we make use of something with this type of scope, closure, but also to understand, what is going on and what else is related in JavaScript in order to make this work. So yes, let's just do a quick introduction to closure, and then we will jump into the workshop. Let me make sure that I'm actually on the right slide. I'm not. Of course I'm not. Yeah, I'm gonna start over. I'm gonna start over. This is why it's better to do this with participants. Okay, let me start over. Hi, everyone. Welcome to Codesmith. My name is Laura, and today we're going to be talking about closure in JavaScript. This is a very esoteric concept in JavaScript. It has to do with scope and what sorts of things that we have available to us, what sorts of data that we have available to us in code, and where it comes from. Closure is the concept that empowers some of the functions that you may be familiar with, like once and memoize, but it's also behind the scenes with a lot of other really important and impactful patterns in JavaScript, like the module pattern and asynchronicity. So before we get into exactly what closure is and how it works behind the scenes, we are going to build some shared vocabulary through a practice of diagramming, and through reviewing a few fundamentals that are really important to understand in order to take this kind of confusing concept and put it into our own realm of understanding. So the principles that we're going to diagram through are going to include functions, the thread of execution, and memory. So let's look at each of these at a high level, and then we'll go through a practice diagram. No closure on this screen, spoiler alert. We'll build our familiarity with this, and then we'll get into some of the characteristics about JavaScript that makes closure possible. So first, let's start with functions. As I go through the workshop today, I would encourage you to try and answer the questions that I ask. If you need to pause the video and think about it for a moment, feel free to do that. Building a practice of trying to come up with an answer, even if you're not sure whether or not it's right, is so important when we are writing code and building out our understanding of these concepts. So my first question is, what is a function and what is it used for in JavaScript? So first question, feel free to pause the video, come up with your own answer, and then start again and see if it matches what I'm about to say. So a function is a set of instructions that we can run over and over again. There are a few important characteristics of functions in JavaScript. They can have a label or a name. It's not required, but they can. And then there's also the function definition itself, the code that we will run along with its parameters and the actual code block itself. So we have a function here on the screen. Multiply by 2 is a function, and we are defining it in this block of code, and we are executing it with parentheses on this line of code as well as on this line of code. And I think it's important to note that we can reuse this function over and over again as many times as we want by invoking this function definition. So functions in JavaScript help us keep our code dry in that we don't have to rewrite code that we want to run over and over again. Instead, we can invoke a function and just write that code one time. Functions are going to be a key component to using closure in JavaScript. Another key component to understand today is the thread of execution. JavaScript runs code like we read in English, left to right, top to bottom. The thread of execution keeps track of where JavaScript is in the execution and the reading of that code. So the thread of execution is something that we're going to keep track of in our diagram, which frame on the call stack is the thread of execution executing code in, and how can that help us know what scope, what variables, what memory JavaScript has access to. Finally, last but not least, memory. This is so important, right? As humans, we have memory. We can remember that our friend's name is Deborah, and Deborah's name references some data, which is our friend Deborah, right? The same thing is true here. JavaScript needs some label for some information or some data in its ecosystem, and the way that it's going to keep track of that is in its memory. So we have different types of memory and different types of scope in JavaScript, and today we're going to talk about the global memory. We'll also talk about function memory or local memory, and we will talk about closure, which is another way to persist some data in JavaScript. Okay, so we're going to take this block of code and we're going to diagram through it. Again, there's no closure in this code. So if you're looking for it here, you're not going to find it. The purpose of this is to build out our understanding and build out our diagramming practice so we can take that understanding and dive a little bit deeper into a little bit of a more nuanced topic, which is closure. So let's move to the diagram. And I just want to orient you as to what we're looking at. So when we're executing code and when we're diagramming at Codesmith, our goal is to kind of put on the role of JavaScript. How does JavaScript go through this code line by line and execute it? What does it keep track of in its memory? What does it use, or what does it execute in its execution context? And also, how does it keep track of that? So as I said from the last slide, we will keep track of a thread of execution here, which is I've abbreviated as TOE. And we'll also keep track of the call stack. So the call stack is going to hold any of the code that JavaScript is executing at any one time. The global execution context will always sit at the bottom of the call stack, and any functions that we invoke will be pushed onto the call stack and popped off when they're finished. Okay, we also have our global memory. Again, this is where we are going to keep track of our data along with the labels for that data. And let's put on our JavaScript hat now and go through this code line by line as JavaScript would. So we're starting with the thread of execution in the global execution context, and we're going to start here on this top line. Again, you're watching this workshop, right? If you were coming to one of our live workshops, you would have the opportunity to practice this live with other folks, which is a great way to learn and to build your comfort level and reasoning skills in the moment. But feel free to draw out this diagram yourself, to walk through this code yourself, and then come back and see how close you were or what you might change in terms of your understanding and how JavaScript would walk through this code. I'll walk through it for us now. So JavaScript is going to start on the top line, and it's going to declare a variable with the label num in global memory and set its value equal to 3. So let's do that. We have a label for the value of 3 in global memory. So now JavaScript will know whenever it needs to access num further down in its code, it will check global memory for the label num and find the value 3. Okay, so JavaScript has executed this line. We move on to the next line. Here, JavaScript is defining a function with the label multiply by 2. It's going to define this in global memory, and it's going to wrap up all of the function definition and store it in memory. So we're not invoking this function definition here. We're just storing this definition so JavaScript can access it and use it later when the function is invoked. Big distinction, an important distinction between defining a function and executing the function. So the name of this is going to be multiply by 2. So let's write that out. And again, its value is going to be a function definition. And when we are diagramming this out and we want to represent a function definition, we will use this symbol, a box with an F on it and an arrow through it. This is going to symbolize a function in our diagramming. JavaScript does read from left to right and top to bottom, but when it defines a function, it will wrap all of this up in our function definition box. It will not run that code. Instead, it will move down to the next executable line of code, which is right here, where we are defining a constant with the label output in global memory, and we are setting it to the evaluated result of invoking multiply by 2 with the argument num. So let's break this down. First thing JavaScript is going to do is create this label, and it's going to be equal to whatever the invocation of this function resolves to. First thing JavaScript needs to do is find out what is this label referring to. It will check in global memory and find out that it is a function definition. Then we are going to invoke that function definition, which I know we're doing an invocation here because there are parentheses, and we're passing in the argument num. What is num? JavaScript's going to check its memory and find num to be 3. So we're invoking multiply by 2 with the argument 3. Whenever we invoke a function in JavaScript, we are going to open an execution context, and we're going to push that to the call stack. So let's do that here. We have our function invocation, multiply by 2 with the argument 3 on the call stack. The thread of execution is going to weave its way into this new stack frame. And let's also draw that here, right? Because we need a place to execute this code. So we're going to draw a function level execution context for multiply by 2 with the argument 3. And every execution context, just like our global execution context, is going to come with its own memory, a place where JavaScript can store variables and data and keep track of them just like it does in global memory. So we have our local execution context, a place where JavaScript can execute code. And we also have our local memory. The first thing that JavaScript is going to do anytime it has opened a new execution context, anytime it has pushed a new stack frame onto the call stack and moved the thread of execution into it, is pair the function's parameters and arguments. A parameter is a placeholder, and it's defined in a function definition in these parentheses here, for the argument that will be passed in when it is invoked. So again, a parameter is a placeholder for an argument. A mnemonic that I like to use to remember this is parameter, placeholder, P and P, argument, actual value. What is the actual value we are invoking the function with? So in this case, our parameter is input number. So in our local memory, we will denote the label of input number. And what is our actual argument? Well, the actual argument is 3. So in this memory, in this local space, anytime we see input number, its value is going to be the data point 3. Okay, so we've paired our parameters and our arguments. And the next thing that we're going to do is move into the function definition itself, into the code block. And so the first thing that we're going to do within this local execution context is define a constant with the label result, and we'll do that in local memory. And we're going to set this equal to input number times 2. So let's do that math in our execution context, right? We're executing some code here. So what is input number? Well, JavaScript is going to check its memory. Input number is 3. And 3 times 2 is 6. So in this local memory, the result is going to be the number 6. JavaScript moves on to this next line, and here we've hit a return statement. So a return statement is how we return some data or functionality from a function back into its parent context. So in this case, we are returning result. So JavaScript will check its local memory. What is result? Result is the number 6, and we're going to return that where? To the place that the function was invoked. So remember, multiply by 2 with num, which is 3, was invoked to be the evaluated result, or its evaluated result will be the value of output. So this result is going to be sent to output. Once we return out of a function definition, or we've run all of the executable code there is to run, that is eligible for garbage collection. So I'm not going to erase this here because I want you to be able to see what happened, but I am going to exit out, and we can imagine that it has been cleared from JavaScript's memory. It has been popped off the call stack. The thread of execution is now back in the global execution context, and we're ready to run some more code there. This line is done. So JavaScript can move on to this next line. So on this next line, what's happening? We are defining a constant with the label new output. And where are we defining this? Back in global memory, right? Our thread of execution is back in the global execution context. So let's add that to our global memory. And the value of this is going to be the evaluated result of invoking multiply by 2 with the argument 10. So we're going to do the same thing that we just did, but in a new execution context because this is a new function invocation. What does JavaScript do? First, it checks its memory. What is the value associated with multiply by 2? It is a function definition. So we are going to invoke that function definition with the value of 10. So let's first push this onto the call stack. We'll weave the thread of execution in. And we'll open an execution context so that we can figure out what is the evaluated result of multiply by 2 with the argument 10. So I'm going to label this here so that we have it. Multiply by 2, this time with the argument of 10. And just like we saw before, we will set up a local execution context. You'll also hear this referred to as a function level execution context. And this will have a space in which to execute code and also its own local memory where we can store some data and their labels. Okay, so think back to just a moment ago. What is the first thing that we are going to do when we open a local execution context? We're going to pair our parameters and our arguments. So our parameter here, our placeholder in the function definition, is input number. And the value, the argument that we're passing in to pair with this parameter is the number 10. So input number in this context is 10. Notice how input number was 3 in the previous execution context. It can be something different here. This is part of the power of functions. Input number is 10. So we have checked that step off. We've paired our parameters and arguments. Now we are going to move into the function definition itself as we execute this code. So the first line of this is to define a constant with the label result. And we're going to set this to equal input number. What is input number? JavaScript will check its memory and see that input number is the number 10. So 10 times 2, right? Input number times 2. 10 times 2 is 20. So result is going to be 20. We've executed this line. Let's move on to the next line where we hit a return statement. We're going to be returning result, and result is 20. Where are we going to be returning this to? To where the function was invoked. So new output in global memory will get a result of 20. We've returned from the function. This means that this function is eligible for garbage collection. We can pop it off the call stack and weave our thread of execution back into global memory. There is no more code left to execute here. We have finished the code that has been provided for us as JavaScript to figure out. Okay, so again, what we're really focusing on here is not closure. We're focusing on some concepts that we're going to need to understand, some foundational level concepts, in order to dive into some of the characteristics that make closure possible in JavaScript. So we have our functions, in this case, multiplied by 2. We have our memory, where we can store data and give it some name so that we can reference it later, whether that's global memory or local memory. We have our thread of execution, which helps us keep track of where in our code JavaScript is executing, in which context. And we also have our call stack. And let me just add a label for that here so we know what it is. Okay, so these are the foundational pieces that we're going to be kind of diving into in a little bit more detail over the course of the workshop. We're going to start with talking a little bit more about functions because functions are critical to making closure possible in JavaScript. One characteristic about functions is the way that they're stored in memory. Functions can have multiple names, right? We said before functions are sets of instructions, they're blocks of code that we can save in memory and we can run over and over and over again. There are two parts to defining a function. There is the name or the label. In this case, this function has the label multiply by 2 when we define it. And there's also the code or the definition itself. So it's parameter and the code block that we're going to run whenever we invoke this function via its label. One thing that's interesting to note here is that behind the scenes, when we define a function, and we assign it a label, that label is pointing to a reference in memory. It's pointing to a place in memory where this function definition is stored. And what that means is that we can actually give this function definition multiple names, and it will point to the same place in memory. When you think about this and how memory works in JavaScript, and when we're talking about these references to places in memory, you can think of it in the same way that you might say, Laura lives at 123 Main Street, which would be my address, my fake address. We could call it Laura's house. We could also call it Phil's house because Phil also lives at the same place. The same place on the street can have multiple labels, Laura's house, Phil's house. It can also have an address, and it does have an address, 123 Main Street. The same thing is true here. So we can define this function multiply by 2. It will get an address. For the sake of the example, we can say its address is 123 Main Street. And then later on in the code, we can give a new label, an additional label, to whatever is stored in memory with the label multiply by 2, and its address in memory will be the same, 123 Main Street. Let's explore this in our diagram, in our diagramming practice, to further understand how this is happening and what's going on here. Okay. So we have our global execution context, we have our global memory, we have our call stack. Our thread of execution is starting in the global execution context as always. Let's walk through this code line by line as if we were JavaScript to understand what's happening here. So step 1, on the first line, we are defining a function. We're giving it the label or name multiplied by 2. We're going to be defining this in global memory. Why? Because our thread of execution is in the global execution context. So let's do this. Let's use a different color this time. Multiply by 2 is going to be a function definition. And remember, all of this function definition is wrapped up and stored inside this function definition box. And we can now move on to the next line of executable code, which is going to be this one here. We're defining a constant with the label output. And we're assigning it to be the evaluated result of whatever multiplied by 2 is. So JavaScript needs to check its memory and see what is the value of this label. It is this function definition. Great. We're going to invoke that function definition with the argument 9. So we're invoking a function here. What's the first thing we're going to do? We're going to push it to the call stack. So multiply by 2 with the argument 9. Our thread of execution is going to move into this execution context. And we're going to open up a execution context in which to evaluate this code. So we have multiply by 2 being invoked with the argument 9. What is the first thing that JavaScript does whenever it opens a local execution context? The first thing JavaScript does when it opens a local execution context is pair our parameters and our arguments. So what is our parameter in the function definition for multiply by 2? Our parameter is input number. So in our local memory, and I'm going to abbreviate local execution context from here on out, but in our local memory, we are going to pair our parameter, input number, with our argument, which in this case is the number 9. So in this invocation, in this context where we're executing our code, anytime we see input number, it will be equal to the number 9. Okay, what does JavaScript do next? It moves to the first line of executable code in the function definition itself, where we are defining a constant with the label result in our local memory, because that's where our thread of execution is. And we are going to set this equal to the product of input number times 2. So JavaScript has to check its memory. What is input number again? It checks its local memory and finds input number is the number 9. We're going to multiply 9 times 2, and we will get 18. So our result is 18. We've completed executing this line of code. We can move on to the next line, which is return statement. We are returning result. Where are we returning result to? To wherever this function was invoked. In this case, that is on this line right here. So output in our global memory is going to be the value of result. Notice how we can send some data from this local execution context out into another execution context, out into our memory. So we have returned from this function. That means what? What needs to happen? A couple of things. First of all, it's eligible for garbage collection. So let's mark that off here. This means JavaScript doesn't have to keep track of it in its memory anymore. It has no memory that input number was 9. It doesn't need to remember that. Its memory can be freed up for other things. What else happens? We need to pop this stack frame off the call stack. And we need to move our thread of execution, weave it back into our global execution context. Okay, so even though I am going to leave this here, JavaScript has no memory that this ever happened, that this ever existed. We can go on and use multiply by 2 in other contexts without any of this being affected. Okay, so we have just finished running this line. JavaScript moves line by line. Here's this next line. This one is interesting. This is where we start to think about that characteristic of how functions are stored in JavaScript's memory. So we are defining a new constant with the label, very long label, new label for multiply by 2. We love it. It is semantic. Okay, so here we go. New label for multiply by 2. Okay, and what is the value of this new label? The value of this new label is this. It's the function definition for multiply by 2. JavaScript is going to check what is the value of this in memory. If it was the number 4, then new label for multiply by 2 would be the number 4, but that's not what it is. It is this function definition. So what that means is that this function definition has 2 names. We can refer to it as multiply by 2, like we did here, or we can refer to it as new label for multiply by 2, and they will function the same way. So we have completed this line. We can move on to the next line. And on this line, we have a constant, fresh output, and we are back in global memory. So this is going to be defined in global memory. And its value is going to be the evaluated result of this function invocation. So what does JavaScript do? Again, reading left to right, the first thing it's going to do is check its memory. What is the value of new label for multiply by 2? The value of this is this function definition. Great. We're going to invoke this. I'm not going to be able to fit this whole label in the call stack, so I'm going to abbreviate it to new label for now. But let's push this to the call stack. The argument that we're passing in this time is 10. We are going to move our thread of execution into this execution context that we need to evaluate. And we're going to open an execution context in which to execute this code. So new label for multiply by 2, Again, I'm going to abbreviate for space here, passing in the argument 10. Let's open up the execution context. Okay, we'll give it a local memory and also a place in which to execute code. Our local execution context, LEC, and our local memory. So what is the first thing that JavaScript does when it opens a local execution context? No matter what, every time, it's going to pair parameters with arguments. So again, this function definition is here, right? Here is our definition. Why? Because new label for multiply by 2 is the value of whatever's in memory at multiply by 2, which is this function definition. Okay, so that means our parameter here is input number. Let's add that to our local memory. What is the value of input number in this context? It is the number 10, because that is what we are passing into this invocation of this function. Okay, so JavaScript knows in this context, whenever we see the label input number, it will be equal to the value 10. And JavaScript will know this by checking its local memory anytime that it sees this label. All right, we've paired our parameters and our arguments. Let's move into the first line of our function. We are defining a constant with the label result in our local memory. Why are we defining it in our local memory? We're defining it in our local memory because that is where the thread of execution is at the time that we run this line of code. So what should the value of result be? It should be input number. JavaScript checks its local memory and finds input number to be the number 10 times 2, right? We're looking at this line right here. So input number times 2 is 20. So result in this context is 20. We have finished running this line of code, and we can move on to the next line. The next line says to return result. Where do we return the call of a function to? We return to where the function was invoked. And in this case, that is the label fresh output in global memory. So 20 is leaving this local memory and going back out to global to be stored with this label. Okay, we've returned from a function. What does that mean? It means that we can mark this as eligible for garbage collection. JavaScript doesn't have to keep track of it anymore. It can free up that memory, those resources to execute other code. It also means that we are going to pop this stack frame off the call stack and that our thread of execution is going to move back into our global execution context. Okay, we have no other code left to run here, but this is a really helpful example for us to see that one function, it can have multiple names. This one function definition could go by multiply by 2. It could go by new label for multiply by 2, just like an address in the physical world might have multiple ways that we refer to it. An address in memory in JavaScript can have multiple references to it as well. Interesting, right? Okay. Let's start to talk about a little bit and get into how this might connect to Clojure. So when our function gets called, and we've seen this, we create a live store of data, our local memory. You might also hear this referred to as the variable environment, right? We are going to keep track of any data that's stored, that's declared in that function definition within the local memory. When the function finishes executing its local memory, it's deleted, right? The only thing that we sent back to the global memory was whatever was returned. Let's just look back at that for one moment. So in this case, for output and multiply by 2 with the argument 9, the only data that was persisted was the number 18, And for a new label for multiply by 2 with an argument of 10, the only data that we retained that was persisted was the argument of 20, and that's because of this line right here. We specify what we're going to return from the function so that we can persist it beyond the execution context lifespan, even though that these have been garbage collected. Okay, so what can we take from this? What we can take from this is that if there's something that we want to persist, we need to return it, okay? We need to return it from the function definition. So what does this have to do with closure? Well, we're not quite there yet, but I promise we're getting there, okay? So let's continue to step towards what we're getting at. What we want to think about is, what if functions had some way to continue to update that data, to continue to keep track of data in between function calls instead of them being completely isolated? Remember, JavaScript had no memory. The input number was ever 9 in this context when it moved into this function execution. So what if we could do that? That is really what closure is all about. It's about giving our function definitions a persistent memory. And there's all sorts of names for this, and we'll get into that in a few slides. What this starts with is the return value from a function. And specifically, we can return data from other functions, but we can also return other functions. Let's explore this in a diagram. So remember, we said earlier there are 2 parts to defining a function: the function's name or label. This is actually optional. You can make an anonymous function as well, but this is one part. And then also the function's code, its definition. So we have a new code snippet here. Let's diagram through this and explore what it would be like to return a function definition from another function. Okay, so we have 2 function definitions pictured here. We have our function definition for create function. We also have our function definition for multiply by 2. Before we go into this and diagram it as if we were JavaScript, I just want to make that super clear. So let's just highlight some things here. So there's the function definition for create function in purple, right? Everything in purple is encapsulated in this function definition for create function. But we also, let me use a different color here, we also have a function definition for multiply by 2 that happens to be defined within this other function definition. 2 function definitions, 2 labels, not 2 labels pointing to the same definition like we saw in the previous example. These are distinct. Okay, with this note in mind, let's diagram through this as if we were JavaScript. So the first thing that JavaScript is going to do is what? It's going to create a function with the label create function in the global memory. So the value of this label is going to be a function definition for create function. And you know what? Maybe we should do this in purple to match the colors that we've highlighted here. So let's do that. Okay. So create function is going to be this function definition. Okay. Remember, when JavaScript is defining a function definition, it is not invoking this code, it's not executing this code. Instead, it is wrapping it all up and putting it in memory with its associated name or label. So where does JavaScript go from here? What's the next line of executable code? It's this line. So let's execute this line of code. We have a constant with the label generated func. Generated func. And what is this going to be equal to? It's going to be equal to the evaluated result of invoking create function. So whatever is returned from create function is going to be what generated func is. Notice that this is different than what we saw a few diagrams ago where we just gave a function another name. The distinction here is that we are invoking this function. So this is why generated func isn't just create function's function definition. It is the evaluated result of that function because we are invoking it. Important distinction. Okay, we're invoking a function. What does that mean we need to do? We need to open up an execution context for create function, and we need to push it to the call stack. Okay, our thread of execution will weave its way into this execution context. And let's create that execution context here. Interesting thing that we haven't seen in our diagrams yet so far is there are no parameters here. There are no parameters, there are no arguments, but JavaScript is still going to check, are there any parameters and arguments to pair? In this case, no, there's not. So we will move on to the next line. Okay, no arguments and parameters to pair. So we go straight on to the next line. And what are we doing here? We are defining a function. Where are we defining this function? Well, where's our thread of execution right now? It's in the create function stack frame. So we are going to define this in the local memory of create function. The label for this is multiply by 2. And its value is going to be this whole function definition that's inside these brackets, right? So this is going to be a function definition. That is the value of this label in this context. This is not executable code. It is function definition that we have not yet invoked. So we move on to the next line of executable code, which is right here, this return statement. We're going to return whatever value is associated with the label multiply by 2. JavaScript will check this. What is that? It is this function definition in yellow, okay? So that is what gets returned out to the label generated func. It is the function definition associated with multiply by 2. Interesting, interesting. This is an example where this function definition has two names. It has the name multiply by 2 in local memory, and it has the name generated func in global memory. Because we have returned this, we do all of the normal things that we do when we return from a function definition or from a function invocation, excuse me. So what are those things? We are going to mark our local execution context as eligible for garbage collection. We're going to pop the stack frame off the call stack, and we're going to move the thread of execution back into global. Okay? JavaScript has no memory of this anymore. Great. We have finished running this line. What happens next? We go on to the next line of executable code, where we are defining a constant in global memory, because that's where our thread of execution is, with the label result. And we are setting result equal to the evaluated result of invoking generated func. JavaScript will check memory and say, what is generated func? It is this function definition, the one we've highlighted in yellow here, with the argument 3. Okay, so what do we do when we invoke a function? Several things. First, let's push it to the call stack. Next, let's move the thread of execution into this execution context. And let's create the execution context so that we can execute this code. So generated func with the argument 3. And just like all of our other execution contexts, this will both have a place to execute code we'll put over here on the left, the local execution context, and also a local memory. What is the first thing that JavaScript does when we open up an execution context? It pairs our parameter with our argument. What is our parameter here? Our parameter is num. Num is our placeholder in our function definition for our argument, our actual value. So in local memory, num is going to be equal to the value of 3. Now that we've done that, we can execute the code inside of our function definition. And we're really only doing one thing here. We are returning num times 2. So JavaScript looks for what is num. Num is 3. 3 times 2 is 6. We're not even storing this in local memory at all. We are just returning this product, right? Where are we returning it to? We're returning it to the site where this function was invoked. So where was generated func invoked? It was invoked here to be paired with the label result. So 6 is headed back out to global memory. And we can do all of the normal things with this execution context because we have returned from it. We've executed all the code there is to execute inside. We will mark it as eligible for garbage collection. We will pop it off the call stack. We will move the thread of execution back into global. Okay, and our code has run. So this is still not yet closure, but we're getting there. We're getting closer because in this example, we are returning a function definition from another function. And this is going to be key to creating a closure. Okay. Let's take this one step further. When we define a function and where we define a function, the context in which we define a function is going to determine what variables our function has access to when we invoke the function. But it's where we define it that determines what access it has. So let's look at this example and explore it. We have two function definitions here. We have a function with the label outer. We also have a function with the label increment counter. We're only going to call outer in the global context, but within the local context of outer, we have another function invocation. So let's diagram through this and see what happens and how increment counter is going to access this variable counter. Okay, I've put the code down in the left-hand corner here so we have a bit more space. And let's diagram through this as if we were JavaScript. What happens first? First, JavaScript is going to define a function with the name outer in global memory. And you know what, we'll color code here as well because I think that was helpful last time. So let's just mark this whole outer function definition, and let's also mark this function definition as well. Let me make that a bit more clear. Okay, so we've got these two function definitions. One is actually defined inside the other. Okay, so the first thing that JavaScript does is define outer. Its label is this entire function definition. And this is all saved in global memory. Why in global memory? Well, that is where the thread of execution is. It's where it always starts. And so any code that we run in global memory is going to save its variables here. Okay, so we have this function definition, everything in purple, saved in global memory. What is the next line of executable code? It is this last line. It's the execution, the invocation of outer. We're not saving this to be associated with anything. So let's see what happens when we execute outer in our global execution context. What is the first thing we need to do when we invoke a function? Well, let's push it to the call stack. And let's weave our thread of execution into this stack frame. And let's write up our execution context for outer. I'm gonna make this one nice and big here. Okay, what is the very first thing that JavaScript does whenever it opens an execution context? Take a moment and think about what that is based on what we have said in our diagrams so far. So the first thing that JavaScript does is pair its parameters and its arguments. Are there any parameters and arguments to pair in this situation? No, there are not. So nothing that we need to store in local memory from the outset. Let's move on to the next line, the first line in our function definition, where we are going to declare a variable called counter. And where are we going to declare it? Well, our thread of execution is in the outer local execution context. So we're going to pair it in outer's local memory. So in outer's local memory, counter will have the value of 0. Okay, what happens next? From here, we go on to the next line where we define a function with the label increment counter. Where are we defining this function? We're defining it in local memory because that is where our thread of execution is. So increment counter will be defined here, and its value will be a function definition. Why will it be a function definition? Because that is the value associated with this label as we define it here. Okay, everything in yellow wrapped up and stored in our function definition label associated with counter. We move on to the next line of executable code, which in this case is increment counter. So JavaScript is going to check what is the value of increment counter. It's this function definition. Here are these parentheses, so let's invoke it. So we haven't yet garbage collected outer. So what happens in this case is that we will do all of the normal things. We will push increment counter, which I'm going to abbreviate for the sake of space, to our call stack. We will weave the thread of execution into that execution context, into that stack frame, and then we will open up a new execution context. But because we haven't closed our outer execution context yet, we haven't yet finished all the code that there is to run inside of that function definition, we're going to open this execution context within this outer execution context. Okay. So let's do this. Again, this is for increment counter. And just like all of our other execution contexts, this is going to both have a place in which to evaluate code, an execution context, and also a place to store data, a local memory. Okay, what's the first thing that we do? The first thing that JavaScript does when it opens an execution context, it's going to check if there are parameters and arguments to pair. And in this case, there are not, right? There are no labels or values passed into the parentheses. So nothing to store in local memory right off the bat. The next thing we're going to do is evaluate the first line of code in the function definition. And here we are. So this is interesting. Remember, up until now, JavaScript has been checking the memory of the execution context that the thread of execution is pointing to. And this is true of JavaScript. That's the first place it's going to check whenever we see a variable name. So here we are in this yellow execution context and its associated yellow memory. Is there a label counter here? There is not. So where do you think JavaScript goes next to look for this label? It's going to check this execution context. And it does find counter here, and it will increment it by 1. That's what the double plus means here. is that to take whatever the value of counter is and add 1 to it. It's the same as saying plus equals 1. And so we make this change, and this is the only code that is executable within this function definition. And so even though there's no return statement, we will implicitly return from this function definition because there's no more code left to run. So it returns undefined. There's nothing specific that we've said to return, but we can mark this as eligible for garbage collection. We can pop it off the call stack. We can move the thread of execution back into the parent level execution context, which is outer, which is where increment counter was invoked. And in this execution context with its local memory, we have incremented counter. Okay, let's move on to the next line of code. There is no more executable code after increment counter's been evaluated, so we can also mark this as eligible for garbage collection, pop it off the stack, and move our thread of execution out into global. And there's no more code to execute here either. We have reached the end of our code. Okay, so this feels a little bit intuitive, right? Like if we can't find the label that we're looking for within our own local memory, it kind of makes sense that we would check an execution context above us, or we would check global memory for that label to see what it is before JavaScript says, oh, this is undefined. And in this case, we did find it here. Oh. Friends, this is possible because of closure. This is possible because of closure. Counter is available as closure, as a closure. And to really illustrate this, we're going to go through one more diagram, and we're going to look at this very specifically in a case where our inner function is not invoked within the execution context it was defined. So let's look at that, right? This looks very similar to what we just saw, but instead of invoking increment counter within our outer execution context, we are going to return its function definition, which we saw as possible from our previous diagrams. We are going to then invoke outer, whose evaluated result is the function definition being returned. So my new function will be this function definition. And then we're going to invoke that and see how we can access counter. How is this possible? What is closure? We're at it. We got there, friends. Okay, let's go into it. And again, before I go to the diagram, I just want to highlight this one more time because it's so important. Where you define your function determines what variables your function has access to when you call it. It has much less to do with where you call it. It is all about where you define it. Okay. With all of that in mind, our last diagram of the workshop, and we'll also talk about some fun thought experiments to tackle from here. Okay, so again, this looks pretty similar to what we saw before, but let's walk through it as we did before, as if we were JavaScript line by line. What is the first thing that happens? Actually, and let's do what we've been doing because it has been so helpful to visualize where the bounds of these function definitions are, right? So we have our outer function definition, and the return value from our outer function definition is increment counter, right? And then we also have our inner function definition here. Okay. So as JavaScript, the first thing that we're going to do is the first thing in the code, the very first line. We're defining a function. Where are we defining this? In global, that's where our thread of execution starts. This function label is called outer, and let me color code it purple so that we continue with our pattern here. This function's label is outer, and its value is its definition itself, everything wrapped up in this symbol that we can use and reference when we're ready to invoke it. So the next line of executable code from here is where? we're going to declare a constant with the label myNewFunction. And we're going to set this equal to the evaluated result of invoking outer. So whatever is returned from outer, and as humans, we can see that it's going to be increment counter, but as JavaScript, we have to go through things line by line. Whatever is returned from outer is going to be the value of myNewFunction. Okay, so what do we need to do whenever we invoke a function? First, we're going to push it to the call stack. We are pushing outer to the call stack. We are weaving the thread of execution into this new execution context, which we will open up here. So we need to evaluate the invocation of outer. This is not a new question. What is the first thing we do when we open an execution context? We are going to pair what? Our parameters and our arguments. So we have a local execution context for outer, and we have a local memory, which is where we'll store our parameters and arguments. Are there any parameters and arguments to pair here? There aren't, right? There's nothing in the parentheses. So we move on to the next line of code in the function definition itself, which is declaring this variable, let counter equal to 0. Where are we declaring this variable? Well, our thread of execution is in outer. So that is the local memory where we will store this. Counter is equal to 0. Okay, what is the next line of code? We are defining a function. Where are we going to define this function? We're going to define it in the local memory of our execution context for outer, because again, that's where our thread of execution is. The label for this is going to be increment counter. And its value is going to be the function definition, right? Everything that we have defined here in these braces and brackets is going to be stored here. It's not executable code right now, we're just saving it so that when we invoke it, we can use it. Okay, so this is stored. So what is our next line of executable code? We're going to move down to this return statement. And what are we returning? We're returning whatever is associated with the label increment counter. And so we go to memory and look at what is associated with it. We will see that it is this function definition. And so ultimately, this is going to be returned out to where outer was invoked to be paired with the myNewFunction label. Okay, let's do that. There is no more code left to run in outer. We have returned from outer, so we are going to mark it as eligible for garbage collection, and we are going to pop it off the call stack, and we are going to weave our thread of execution back into the global execution context, and we're going to move on to the next line. Does anyone see potential issue with what has just happened, particularly given the definition of increment counter? Let's see what happens next. Okay, so we've run this line. We're going to move on to this next line, and this is invoking myNewFunction. We know it's an invocation because we see our parentheses here. What is myNewFunction? JavaScript is going to check its memory and see, yes, it is this function definition. Anytime we invoke a function, we are going to push it to the call stack. I am going to abbreviate this to myNewFunc here for the sake of space. We are going to weave our thread of execution into this execution context. Let's draw that execution context here. Make it a little smaller. What is the first thing that we do when we open an execution context? What do we need to pair? We need to pair our arguments and our parameters. Are there any arguments and parameters to pair here? there are not, right? There's nothing defined, no parameters defined in our function definition, and no arguments passed in my new functions invocation either. So we'll move on to the next line. And that next line is counter plus plus. And where is the first place that JavaScript is going to check for this label? Remember, our thread of execution is in my new func. So the first place it's going to check is its own local memory. Is there a label counter here? There's not, right? Then maybe it might check global memory. There's no label for counter here either. So how are we going to increment counter, which is actually in a execution context that was garbage collected, right? We marked this as eligible for garbage collection. We popped it off the call stack. It doesn't exist anymore. JavaScript doesn't have to keep track of it anymore. It's freed up those resources for other things. So this is where closure comes in. Okay, remember, where you define a function determines what variables it's going to have access to. Where was increment counter originally defined? It was defined within the context of outer. What this means is that any variables from outer's memory, from outer's variable environment, that increment counter is going to need will actually come with it when it is returned. Remember, we're returning increment counter from this context. So when we do that, when we return increment counter, we are also returning a special variable environment, a closed over variable environment. So it's not accessible by anything else in global. It's only accessible by this function definition with any variables it needs. Okay, so in that case, it needs access to counter. It also gets not just the label, but the value of counter, which at that time was 0. So with that in mind, let's revisit the order in which JavaScript checks for the presence of things. The first thing it's going to check always is counter in my local memory. Is it in the place where the thread of execution is currently executing code? If it's not there, then JavaScript will check its closure. It will check this closed over variable environment that has come with the function definition when it was returned from where it was defined. And is it there? It is. So we are going to increment it from 0 to 1. I want to make something super clear. We do not have access to counter in global memory. This is not available in the global execution context. It is only available from the function definition of my new function. Okay. Let's see what happens next. So we have run all the code there is to run inside this increment counter function execution context, and just because we want to be consistent, let's just mark this here. Counter was 0. It is now 1. So we've run all of that code. So what do we do when we finish running code from an execution context? We mark it eligible for garbage collection. We pop it off the call stack. We weave the thread of execution back into the next execution context down the stack, the next stack frame down the stack. And we move on to the next line of the code. What is our next line of code? It's another invocation of my new function. Remember, this one is garbage collected. JavaScript does not need it, does not remember it. We have our function definition here that we will reuse, and we also have our closed over variable environment, our closure, that we will reuse as well. So let's do all of the things, right? What happens when JavaScript invokes a function definition? Well, we're going to push a stack frame to the call stack, my new func. Notice how this is distinct from the one we just pushed to the call stack, right? This is its own stack frame. We are going to weave the thread of execution into this, and we are going to open up an execution context. So we are invoking the same function definition again, but this is a different invocation, just like in our very first example when we invoked multiply by 2 multiple times, and they each had their own execution contexts. Every local execution context is going to come with its own local memory. Here's our local execution context in which to execute code. Here's our local memory. What is the first thing that we do when we open a local execution context? We're going to pair our parameters with our arguments. There are no parameters or arguments to pair here, so we can move on to our first line of code, which is counter plus plus. So JavaScript needs to evaluate this, needs to execute this and determine what it is. The first thing it's going to do is look where for the data associated with the label counter. The first place it's going to look is its local memory, but it is not going to find it here. Where's the next place it's going to look? The next place it's going to look is its closure. Does it find the label here? Yes, it does. What is the value of that label? It's currently 1. So what is 1 plus 1? We're going to increment this by 1 to 2. Okay, is there any code left to run within this function? There is not. So what will we do? We will mark this execution context as eligible for garbage collection. JavaScript doesn't have to keep track of these things anymore. We will pop it off the call stack. We will weave our thread of execution back into the next stack frame on the stack, which is global. And we have finished running our code. Some thought experiments to think about here. What would happen if we were to invoke this one more time? Think about it for a moment, make your guesses, even if you're unsure. If you guessed that counter would increment to 3, you'd be correct, right? This variable that we have access to in a closure persists over our function calls. It's a way for us to have what you might hear referred to as a cache of data that we can keep track of over different function invocations of the same function definition. So this is really, really interesting and powerful. Maybe this in particular example doesn't kind of inspire you to build something really complex, but there are really complex things that are built using this concept of closure. And it also goes by a few different names. You may have heard me say closed over variable environment. You also might hear people at Codesmith and in our workshops refer to this as the backpack. There are other names for this as well, which we'll talk about in a moment. But ultimately, there's essentially a bond that is created between the variables needed for the function's invocation from its local environment, where it was defined, to the function definition, okay? And so this bond is all about where a function is defined, right? It gets a bond to the surrounding local environment, the surrounding local memory. And let's be really specific. It has access to the variables that it will need to execute. If there was another variable here, let's make one up. Let banana equal true. Increment counter would not include banana in its closed over variable environment, in its closure, in its backpack, because it doesn't need banana in its increment counter function definition, right? But it would still always have counter if it needs that here. If we wanted to console log banana inside increment counter, then it would also include that. Play around with these things in code, make some guesses about what would be included, what would not be included, and go from there and see how you can further build out your understanding. Let's talk about the different names for this concept. Closure is one, and you'll hear people say a closure. This function has a closure, counters inside of that closure. It also can be helpful to think of this as a backpack. that when the function definition itself is returned, which is an essential part, we cannot create a closure without returning a function definition from another function, or without creating a function definition within another function. When it is returned, it essentially has this backpack with all of the variables it needs to execute when it is invoked down the line. So you might hear it referred to as the backpack. And we'll come back to this in a moment to talk about what this enables. But let's talk about some other names for this first. Closure is a valid name. Backpack is Codesmith specific, but it is getting out there in the world. Feel free to use it. And closed over variable environment, Cove, is another name. If you want to be really fancy, this is also called a persistent lexical scope referenced data, or as I like to call it, the please read. This enables us to maintain this bond to outer's live local memory. It is returned out of outer's function definition. It is attached on the back of increment counter's function definition. Outer's local memory is persisted beyond its function invocation itself, even when its execution context has been garbage collected. There are all sorts of fun things that JavaScript uses this for. The module pattern, when you think about Node.js, Ajax and asynchronous JavaScript in general leans heavily on this pattern of closure to give access to past context variables in new contexts later. It's a pretty powerful concept, and y'all, this is how it works under the hood, right? We are attaching whatever is necessary from where a function definition was defined to the function definition itself so that we can persist that data over time. We're not going to diagram this out, but I do want to talk through it and leave you all with some things to wonder, maybe some things to test yourself. So in this example, we have our outer function definition. Looks the same as what we just looked at. We're defining a counter and setting it equal to 0. We're defining a function with a label increment counter and saving that in local memory. And then we are returning that function definition itself. That function definition is going to come with a closure that will include counter equals 0 inside of it. So when we invoke outer, what are we returning? We are running all of this code and we are returning the function definition of increment counter. So what would happen? This is everything we just diagrammed through. What would happen if we were to run outer again? Okay, we know from what we just diagrammed that my new function makes counter the number 1, and when we invoke it again, it makes it the number 2. What would happen if we invoked outer again, gave it another label called another function, and then invoked that? Would this be 3? I'm going to tell you the answer in a moment. So if you want to make a guess for yourself, pause, think about it, and then come back. This would actually be 1. And this would be 2. And to just add one more thing here, if we were to invoke my new function 2 more times, well, let's just do once here, it would be 3. Look, my new function is this function definition, and another function is from this one. Okay, why do you think this is? Diagram through it if you want, and try and make some guess as to why this is. The text over on the left-hand side might give you some clues, but it can be really helpful to diagram through and confirm your understanding, confirm your guess. Okay? Okay, so y'all, closure, super, super powerful, and it's a foundational concept. A lot of folks make use of this whether it's through the module pattern in Node.js or through asynchronous JavaScript, which is used prolifically across the web and beyond. A lot of people make use of this, but don't understand what's happening under the hood and why we have access to the variables that we do. Again, the key here, I would say two keys. In order to create a closure, we need to return a function from another function. In other words, we need to define a function within another function definition and also potentially return it. But also, the other key is where we define a function determines what variables it has access to, not where we invoke the function. Okay, there are some fun practice problems on CSX if you want to take this concept and put it to use in code, which I highly recommend. Replicating once and memoize are some of those on CSX that you could use. And I, again, would really recommend anytime you attend a workshop, and these are very conceptual workshops and like really driving home your understanding of the concepts, the next best step is always to take that conceptual understanding or even those conceptual questions and test them out in code. If you want to see closure in action, I would recommend using your dev tools in the browser and running some code in the browser if you don't yet have VS Code set up. And then using a command called console dir. This is going to give you access to the scope, the double bracket scope. That doesn't look like scope. Let's try that again. Variable on a function definition. And you will see this will be an array where it will list any closures that a function definition has access to. So let me just be more specific about how you might look at this. Increment counter. So if you were to put this code in your console and run it, and then inside outer, you were to console dir the function definition of increment counter, so no invocation, no parentheses, you would be able to see and expand scopes. And within that is where you will see the closure itself. So it can be really helpful as you're learning these concepts to implement them in code and also get some visibility into what's happening behind the scenes. This is how you can do that for closure. There are other ways as well if you're using the debugger tool, either in the browser or in VS Code, but this is the simplest way to get some eyes on what's happening. And you'll also maybe get to explore some other types of scopes that exist. Okay, y'all. What's coming up next from here? I would really recommend attending one of our live workshops. You'll get the chance to practice your technical communication, walking through these diagrams, learning along with others, learning from their questions, them learning from yours. I would also recommend checking out, if you haven't already, CSX. There are some really great practice problems that won't give you the answer, which is so much more powerful than having the answer in the same place where you're practicing. Once and memoize are great practice problems, but if you want to continue learning in community, our prep programs are really helpful for that as well. I hope that this was helpful. Feel free to reach out with your thoughts on the answer to this, and we hope to see you in a workshop again soon. Thanks, y'all. Bye-bye.